In section 9.4, we're covering a new type of hypothesis test and confidence interval called matched pairs. At first glance, matched pairs questions look really similar to the questions we did in the last section. We're going to have two samples. They'll be made up of quantitative data that we can find a mean and a standard deviation for. However, in a matched pairs question, the data is not going to be independent across the two groups. What that means is that our two groups are linked in some way that makes the two samples similar. For example, you're a researcher for the EPA. You've been asked to determine if the air quality in the US has changed over the past 2 years. So you select a sample of 10 metropolitan cities, and you find the number of days each year that they fail to meet acceptable air quality standards. So year 1 and year 2 are two readings on the same city. I'm going to call them A, B, C, D, etc. If we have a city like city B here, that has a lot of pollution, that's probably going to be the case in both year 1 and year 2. Okay, and same thing with a city that has a low number of pollution, low amount of pollution, like would that be EFG? Okay, so the point being is that the numbers in year 2 are linked to the numbers in year 1. These are not independent of one another, and we could see that all these numbers are relatively close to one another. So we have similar numbers. We don't want to just find the average of all these ones, okay, and compare it to the average of these ones, because that's not going to tell us what we want to know. Okay, instead we want to see how much these values are changing from year 1 to year 2. We're focused on the difference between these two samples to see how much they're changing over time. So here are all the different ways we can calculate standard deviations for every test we've learned, whether it's one sample categorical, that's a p-hat problem, adding in a second sample, and same thing for quantitative tests. The nice thing about a matched pair test is that it's going to be the same thing as a one sample test. We start with two samples, we subtract them, we find the differences, and those differences are the only thing we're concerned about. So that's just the one sample that we're working with. So let's actually work through this problem, and we want to determine, has this air quality changed over the past 2 years? So defining the parameter. We don't care about the groups individually. What we care about is the difference. So we're going to say, instead of just mu represents mu sub d, with that d meaning difference. This is the true mean change in the number of days that the US cities failed to meet acceptable air quality standards over the past 2 years. It's also good to write something like this. So we're saying how we're calculating this difference. Is it the first sample minus the second, or vice versa? Hypotheses. Null hypothesis is that there hasn't been a change. Okay, the air quality is the same across the whole population of cities. Alternative is that there is a change, that difference is not equal to 0. So as I mentioned, we subtract these samples. Once we do that, we don't care about the original data at all. We can just throw out this whole table and work only with these numbers. So we have what's essentially a one sample test, which we covered back in chapter 8. We can find the average, standard deviation, sample size for those 10 numbers. And then we calculate standard deviation the same way we did in the previous chapter, S over radical n. So 11.27 over radical 10, that's going to give us the standard deviation of the sample. Now, all this should seem familiar because we've done this problem before. We're going to find a critical value. It didn't give us an alpha level, so we'll default to 5%. Okay, we have a two-tailed test because that alternative hypothesis is a not equal to sign. 5% alpha. Degrees of freedom is 1 less than the sample size. So 9 degrees of freedom. It's going to put us at that value there, 2.262. Find the test statistic. The setup for a distribution is that, as usual, we believe that the null hypothesis is true. So we believe if we went out to every city in the US and measured all of these differences in how many days last year and the year previously they didn't meet those air pollution quality standards, the true difference is 0, meaning there hasn't been a change at all. Our standard deviation we found in the previous page, okay, and in our samples of 10 cities, we saw a difference of negative 6.7. So would that be unusual to see based on these parameters? So we want a t-score for this difference. Okay, we subtract the null hypothesis. This is pretty much always going to be 0. Divide it by the standard deviation. and we get our t-score of negative 1.88. And we're going to use that t-score to find a p-value. So would it be unusual to see that large of a difference if the air quality across the US hasn't actually changed? So again, it's a two-tailed test, 9 degrees of freedom. Where would this number go on that line? So 1.88, it's bigger than this number, it's smaller than that number, so it's somewhere in between 5 and 10% for our p-value. If we wanted to do this using the critical value instead of the p-value, we take our critical value that we found on the previous slide. That's up here, 2.262. It's a two-tailed test, so that goes on both sides. If we end up with a test statistic that's in that shaded region, we would reject the null hypothesis. Here we got a test statistic of negative 1.88, not in the shaded region. And these two final steps are the same as they've always been. What decision do we make and why? Fail to reject the null hypothesis since the test statistic falls outside the shaded region. If we looked at the p-value, fail to reject the null hypothesis since the p-value is greater than the significance level of 5%. We know it's somewhere in between 5% and 10%, which makes it larger than 5%. Our conclusion, we're writing about the mean change across these two samples. Okay, we fail to reject, so it's going to be an insufficient evidence problem. So there's insufficient evidence to suggest that the mean change in the number of days that U.S. cities failed to meet acceptable air quality standards over the past 2 years is something other than 0. Okay, we can't conclude that that's true because our p-value is too large or because our test statistic fell outside that shaded region. In example 2, let's use the same problem to create a 99% confidence interval to estimate the true mean difference in the number of days that the U.S. cities failed to meet acceptable air quality standards over the past 2 years. Parameter is the same thing, and as noted, we're going to find a 99% confidence interval. Standard deviation is found the same way we did for the hypothesis test. We take the standard deviation of the 10 numbers, which was 11.27, divide by square root of the sample size, we get 3.564. Here's the key information. The average difference of those 10 numbers was negative 6.7. Standard deviation we just found, and sample size was 10. Next step, we want to find the critical value for a 99% confidence interval. Remember, confidence intervals always come out the center of our curve. So that 1% left over is on both of those tails here. Okay, that's particularly important for z-score problems. For t-score problems, we just go to our table. We look up here at confidence intervals. 99%, 9 degrees of freedom, one less than the sample size. So our critical value is 3.250. Margin of error is always the test statistic times that standard deviation. 3.250 times 3.564, margin of error is 11.583. To write this actual interval, we take our average difference and we add and subtract the margin of error. So we have negative 6.7 plus and minus that margin of error gives us an interval of negative 18.283 to positive 4.883. Interpret the interval. We are 99% confident that the true mean change in the number of days that the U.S. cities failed to meet acceptable air quality standards over the past 2 years is somewhere between a decrease in negative 18.3 days and an increase in 4.88 days. Okay, so negative means that it's gone down, positive means it's gone up. We're not sure. We think the actual true change is somewhere in that range. Part H is saying, based on those results, can we conclude that there's actually a difference in the true mean change across all cities in the United States? The answer is no, and the reason it's no is because this interval includes 0. Remember, this interval is about the average difference, and since it includes 0, this interval is suggesting that it's possible that the difference is 0, that in other words, there's been no change across both years.